here is a freshly opened Isight Design Gateway, and just to try to prevent any bad things, I have my little, what is called the demo script for this rubber puck analysis sitting in front of me. Again, I did work this with Isight 5.0 and Abaqus Standard 6.10-1. It could be worked with more recent versions. There's really no problem there. I tend to stick with older versions so that I can hand this out to people who have not migrated to new versions of things yet. Some of the big companies we work with take a while to migrate to new versions of our software. And so again, part of this demo is I know that it just gives customers a really good sense that of how simple this really is. And the beauty of Isight is simply this drag and drop capability. And we can say we're going to do an optimization of something. We go to our solution components or our application components, simply drag and drop them. This example, really purposely keep it very simple so that we focus more on the concept, and certainly tell everyone that you could, and here at the Great Lakes office, we've done things like I was saying earlier with a hyperelastic, viscoelastic, Mullins effect, permanent set, and quite complex Isight process captures or workflows. But to get started and to really understand how the power of the data matcher and the power of wrapping Isight around Abaqus, this gets all the concepts across. So we have our process capture. We go into our Abaqus solution component. We browse, pick our single input file that exists out on our disk, ask it to read that file. It reads down through the input file and quickly shows me these three parameters, and I just click here and say those are three things that I want to use within my Isight process. And you see over on the far right hand side, they have default values as stipulated in my input file. Those are the values that came out of curve fitting, what I'm calling bad data that was tainted by friction. And we're going to try to, knowing that that's overly stiff, can we find much better values through this process? My execution, I typically turn lots of things off so that I'm not distracted later as I'm trying to do this example. And I typically would also tell people that the danger of saving lots of output to the database. In this particular problem, I'm not going to worry about that too much. And also draw people's attention to the fact that this abacus.bat, you might want to come in here and alter that to being a very particular version of Abaqus, or at least make sure the abacus.bat on your system points to the right version of Abaqus that you wanted. I'm not going to change the grid stuff, and on the output, I already have an ODB file generated with 610-1. I'm going to read that file. There's very little output in that file. There's just some history variable for the rigid body that's pushing on the puck, and I'm only going to use the RF2 value of that in the data matching. So I've completed the setup of my Abaqus solution component, and I'll go to my data matching component. So the data matching component is really handy. I immediately saw how useful this could be in all sorts of combinations with Abaqus analyses several years ago, and in fact, I think the Isight team has done a very nice job of updating the data matcher to be even more useful and making it fairly simple to use Abaqus results directly instead of having to go through any intermediate steps. We're going to worry about the target or test data first, and I'm going to drive those as the default says here. I'm going to drive that value from a text file. I'm going to select the file from a hard drive, browse. It's this file right here that ends in .txt. Say next. Yes, the default value of table is correct, so I'm going to accept that default. And now here I've got a little window that helps me tell Isight what it is that I'm going to use. And I'm going to use this time information. So very quickly, and then the handy thing of Isight is all these things can be done so quickly. I'm going to use some time information. And then I'm going to, as it shows up here, the Y data source is also going to be driven from a text file. The default value says use the same file, and that's what I'm going to do here, so I can just accept that default. And again, it's a table of data. So, and I can just click the very first one. I can come down here and say, please use also the last one in that column. And I can say finish. And it nicely shows me a graphic of the things that I've just read in. So that is the force. It's really the force time, but we can think of it as the force deflection since time is very proportional to the deflection here. So I could call it force time, or I could call it force deflection, if you pardon the slight inaccuracy of that. So we've pulled in the target or the test data. We're going to say new simulation. We're actually going to use an array parameter for the values. So we think of that RF2 that we got through the Abaqus solution component as our array parameter, and say next. It's this one right here. We're going to select that RF2 quantity that we have from our Abaqus simulation, and we're going to say next. Very convenient, very easy. I'm going to say, please use the first column as my x-axis. Now, how about y? The y value, I'm again going to use, you could use separate parameters here, and this is very useful when you want to truly use, say, a U2 history variable to drive the x, and an RF, a certain column of the RF to history variable to drive the y-axis. We're going to say next. We're going to say, yeah, we're going to happen to use the same history variable here. We're going to tell it to use a column of information, click on the column, and we're all done. And again, Isight is very nice about the data matching solution component. It's very nice about showing you then the test data and the simulation data, which again is we're going to go to results, data comparison. How do we want to compare that data? And I'm going to choose the y-squared difference here, and if we look off in the far right column, it's got a default value of 6.2 e to the 9, which matches the PowerPoint presentation earlier, and I can say OK. I've dealt with the Abaqus solution component. I've dealt with the data matching solution component. I'll come back up to the optimization process. And as I said in the PowerPoint, I found it very useful to use the Hook-Jeeves. I guess I would say that questions, heavy-duty questions about the choices here, I'm not the right guy to answer questions about that. Okay, so Dick Ritelli asked a question again that in Abaqus Isight you assume friction equals 1 bonded. In reality it was less than bonded, right? No, actually in reality this was a test data that was bonded. We actually, for purposes of, I worked with the test lab that's local here close to me that we do a lot of work with, and it really was bonded. The challenge is, could we make that, Dick asked, could we make the friction coefficient an Isight design variable too, and how would that change the resulting optimum material parameter? I mean, I can imagine we would, but at some point you get too many design variables, and the problem becomes completely not unique. I mean, there's going to be a whole problem here of uniqueness. So we're, again, I could imagine adding more and more design variables like the bulk modulus, like friction, but I certainly have to be far more careful about the non-uniqueness and whether I'm really getting the answer I'm looking for, or just another different answer that happens to match the test data. And I typically would approach that usually by trying to have multiple pieces of test data and dividing them using a kind of a divide and conquer approach of matching one piece of test data and then another. I do want to draw everyone's attention to this relative step size. Again, at one point in time, the default value had been 0.5, and I found that to be a very useful default value, and I find myself routinely changing the 0.02 default variable value of that back to what it used to be, 0.5. I have run this problem with different relative step sizes. It gets in many cases, it gets relatively close to the answer, but not as close as quickly as using this value. So I'm going to use hook Jeeves. I'm taking all the defaults except for that relative step size. I go over to the design variables, and all I have to do is tell it that I'm going to use the C10, 20, and 30 values. As we showed in the PowerPoint, you don't have to set a lower and upper bound, but it can be quite useful. I particularly, because of my experiences with elastomers, I have a sense of what they should be. Sometimes it is, I know this is overly stiff behavior, which is why the upper bound I'm going to set to be 1.9244. I know I shouldn't be going any higher than that because I already know I'm overly stiff in the behavior. And to some extent, if you don't have very much work experience with a particular kind of problem, you might say, well, these are guesses. Or you might have to do some design of experiments, things with Isight first to try to get a better handle on bounds, or you might, in fact, just start with providing no bounds and see where things go. But I have a fairly good handle on what my bounds would be, and oftentimes what might happen is that the solution process pushes me up to one of these bounds, and then I would really know that I kind of messed up and should come back and loosen the bounds further. So I'm going to not do anything with the Constraints tab. I'm going to go to the objectives, and I'm going to say that my y-squared difference was my objective, and the default is to minimize it, and I'm going to accept that. Now, at this point, you could consider that I'm finished setting up this problem. I could save it, and I could run it, but I really like showing people these graph templates, and notice that I've clicked on and focused on the data matcher, and I'm going to go to the graph templates, and I'm going to create two graph templates, a history graph of the y-squared difference. I typically choose logarithmic y-axis because I expect that thing to drop by several orders of magnitude. And it nicely makes a graph that will show while I'm in the runtime gateway. And I'm going to create one other graph, and it's called an array graph. And that array graph is going to be the x versus y of the test or target versus the output of the Abaqus simulation. And with that, I'm finished setting up those two graph templates, and I'll refer back to them later in the runtime gateway. Back to the SimFlow, I could simply come up here to File, say Save As. I start off, oftentimes in these demos, I use something called null.zmf, which is just a ZMF file that has nothing in it. That way, when I double-click on it, it automatically has the current working directory set. I could name this thing anything I want, like Puck, say Save, and of course, come into the optimizer and say run this component. This thing takes about 4 minutes per Abaqus analysis, and we don't really have the time here to sit through and watch this thing run. So another great feature of Isight is this idea of a jobs database, and it's really useful part of this demo to point out to a fairly new customer that jobs database is always available. And I ran this thing just yesterday to make sure I had something that was fresh and was using the particular versions of Isight and Abaqus that I said. And I can say load the job, and it's going to bring up the runtime gateway, and I've basically got the job completely finished. So you get these nice red and black and white checkered flags that give you the same nice feeling of saying that the job has completed at the end of your STA file. And we can quickly go to the history which shows you the history of everything that was happening throughout all of the process of the eyesight. You see right here at the very beginning, the first iteration had the 1.9244 value of C10 and the things that were in your input file. And you also see that the sum of the square difference was 6.2 e to the 9. And as it goes and goes and goes, and it's going to do a default number of 100 or a max number of 100 passes through Hooks-Jeeves optimization. The lowest it achieved was a sum of the square difference of 607. And in fact, these values of C10, C20, and C30 are the ones that I showed you in the PowerPoint. And in fact, they match up very nicely. That's one way of looking at the history of things. Another is to simply change my focus to the data matching component, and you would see the two graphs that I set up. They're relatively small here in the right-hand panel. I would rather go to the Graphs tab, where I can change the size of those things. And again, this is a really nice, I find this to be a very handy feature of eyesight. Very graphical. I like the fact that it's very graphical. We could go back and just click on one of the early iterations where the y sum of the square differences was on the order of 1 e to the 10th, and we see the huge difference in the target value versus the abacus value of the RF2 or just compressive force that it took to compress the puck to 50% compression. Or we could click on any stage along the way, or we can play this thing as a movie with this little symbol down here in the lower right-hand corner, or we can just jump to the very best solution that it was able to find with a 607 y-squared difference. I think with, there's many other things you could look at. Sometimes looking at the summary can be helpful. Again, I tend to focus on just the history, and it is good to tell people about, especially if you use those graph templates, you have to be a little bit careful that that this focus here is on the right component. For instance, if I went back to history, I'm really now showing some history information that's part of not the overall optimization, but the thing that I have sort of my input focus on. Again, the end result is that eyesight finds a very good set of coefficients. I can see that graphically. I can see that by the y-squared difference going down tremendously. I can see that graphically because my target value and my simulation value of the compressive force now line up pretty much line on line. And now I can go back and do the rest of my simulation work with these good coefficients. And I think with that, probably a good time just to open up the floor to questions again.